Brody, tell everyone to go to the new link I posted in Schoology. YouTube kicked me off the last one. Chloe, tell everyone to go to Schoology. Connect to the new link. The first link YouTube kicked me off of. Good morning, 7th grade class of 2021. Welcome back, class. It's good to see you. I'm sorry we had a little bit of a bumpy start. It may have been music that I played earlier, so we've learned our lesson. I don't know what it was. I think it was just a glitch because truly the camera was aimed at the ceiling and the microphone was muted, and yet somehow there was a copyright violation. So maybe someone's copyrighted the ceiling of the All Lab. I didn't know that happened. But anyhow, it's great to see you. Anyhow, here's what we're going to do today. We'll have a quick review of what we've done in the past, and then we'll forge forward a little bit. Stop, talk about logistics, what's due for homework, when we're going to meet back, and then we're going to dialogue a little bit about science fair expectations. All right, is everybody ready? All right. The last that we were together, we were talking about cosmology. I think it's incredibly fascinating. I hope you all are enjoying it as well. And we've been doing the first model of where everything came from, the Big Bang. And we said that the Big Bang had three big parts to it that we had to know to understand the Big Bang. And there was singularity, the ball of everything, the unknown mysterious substance that contained all time, energy, matter, space, and forces, somehow balanced in space in an equilibrium with outward pushing forces equal to inward pushing forces, gravity. Something ended that. At the end of that, it's the Big Bang. The Big Bang happened 13.8 billion years ago. We talked about if we made a timeline that as soon as the Big Bang, let's go back to, remember the Big Bang is lightless. We like to envision the Big Bang as something that includes fire and lightning and, all of the iconic imagery we have when we think of colossal things being birthed, such as the universe. There's nothing bigger. You would think that every possible kind of fire would have been involved, but it was just dark. The universe was so dense. Remember, it's infinitely dense in the beginning, but infinitely hot. It was too dense to even let light out. So you couldn't see it, strangely enough. But yet there it was. So, and it wasn't an explosion. There was no oxygen combining with molecules. They didn't exist. And there wasn't just a single surface expanding out into space. It truly was an expansion. Space-time itself was being born. We said there was a brief period of time at the beginning of the Big Bang called inflation, where everything, the universe expanded at faster than the speed of light. We don't even know how that's possible. It's possible maybe that the speed of light was different back then. Is the speed of light variable? That's a big question. But according to what the speed of light is now, the universe expanded faster than that. And then it suddenly stopped. At breakneck speed, it went back down. Because of that, we created all these this sloshing back and forth, which we call gravitational waves. And those waves back and forth on what was here, and it kind of smashed and pulled everything together so that we had a universe where matter that was being formed was being pushed and pulled into chunks and clumps instead of forming at equal distances to one another. A homogeneous universe would be a universe in which there had been no inflation. All of the particles in the homogeneous universe would have been equal distance from one another. And then a heterogeneous universe is a universe in which the particles are not equal distance. In other words, since some are closer than others, you can generate seeds of gravity that will ultimately build bigger and bigger things, such as stars, planets, black holes, me, and you. So you can clearly see that a heterogeneous universe is vital to the creation of us. It gathered the material into the places that would give birth to solar systems and stars, etc. So we also reviewed, good Lord, we need a lot of energy to do this if we're going to make a universe expand. And remember, as it expands, it's not just getting bigger, it's getting more. There's more universe. So where does the energy that creates this material come from? And we believe it's when the strong nuclear force burst out of the other forces. We believe that they were all at one point united together, one force, kind of like the rings in the Lord of the Rings, right? One ring to rule them all, one ring to guide them, something like that. Does anybody know how that goes? I don't know that. If you know it, put it in chat. But anyhow, the strong force breaks loose. It's the first force that breaks loose, and the energy that it, one ring to rule them all, says Liam Amick. The strong force cuts loose as the force substance changes phase and releases the strong force. The energy that's released becomes the inflation energy. All right. We told you that, one ring to rule them all, one ring to find them, one ring to bring them all, and in the darkness bind them. Liam Amick, thank you so much. I love that. Lord of the Rings. So the universe is still expanding to this day. It's very strange that the universe that we live in is getting bigger and bigger and bigger even today. It wasn't too long ago, within the last 10 years, that scientists were looking at the size of the universe, and they came to a shocking conclusion, and that is that not only is the universe still expanding, but the expansion rate is actually getting faster. And we don't know how, we don't know why, but it's a fact. The universe that you live in, again, that really gives a lot of evidence to the idea that it wasn't an explosion. In an explosion, you'd have an initial burst of energy that is reduced over time, right? A BB on the outside of an exploding firecracker gets thrown only as far as the energy will let it get thrown, and then it's over. The energy's gone. But in our universe, the expansion recently, and recently means within the last million years, has actually started to get bigger. And we don't know what's fueling that. We don't know where the energy is coming from to do that. But you should know that the universe is getting bigger. There's a rate. They actually know how fast, give or take a couple of percentage points. But the most recent rate is how fast is the universe expanding? 71 kilometers per second per megaparsec. All right? A parsec is a unit of distance, and it is a real thing. A parsec is a gigantic unit of distance. A parsec is 19 trillion miles. A megaparsec is 1,000,000 parsecs. So that's an unbelievable amount of distance. Again, a parsec is a distance of 19 trillion miles. A megaparsec is 1,000,000 parsecs. So, in order to see the universe expanding, you have to be looking at a huge chunk of it, a chunk that we need equipment and telescopes to focus on for us. In our everyday life, the expansion rate is really fast if you see it at that scale. At that scale, it's 71 kilometers per second. That's really fast. But because it's only at that scale, by the time you bring it down to the scale that is you and me, space-time doesn't appear to get larger in between us. It is, but infinitesimally. However, when you amp it up to a larger scale, well, boom, there it is. All right. Crazy kids, we're moving forward. That's essentially the Big Bang. There's a singularity, loses equilibrium, expands, and expands faster than the speed of light in the first instant, not even a second, 10 to the negative 35th to 10 to the negative 32nd seconds, highly quisible material. And then, how much faster does it get? It gets larger by a factor of 10 to the 50th. Is everybody good with that? All right. That's essentially the Big Bang without the timeline. That's just the overall concept. 1, 2, 3, 4, 5. How much do you get that? Anybody have any questions? 1, I don't get the Big Bang at all. I have no idea what inflation is. 5 is I get this. Let's move along. Report in for me, please. Who will be first? It's Max. The universe is expanding at 71 kilometers per second per megaparsec. And a parsec is 19 trillion miles. A megaparsec is 1 million parsecs. All right? A parsec, 19 trillion miles. A megaparsec, 1,000,000 times 19 trillion. All right? That's a lot. That's just huge. Awesome. It's good to see everybody in town, too. Good to see your name. I miss you all. We don't know, Leah Neiman. No idea. No idea why or how. No idea what decided how strong. We have to remember here, Leah, here's a really cool thing, and it's for everybody. When the forces branch off, they could be, think of that you have a machine with a dial, and the dial goes from 0 to 10, and that those numbers on the dial represent how strong or how weak the force can be. All right? So as these forces pop into being, they could be anything. The strong force could be the weakest force. The strong force could be 1 billion times stronger. Gravity could be 1,000 times stronger. Gravity could be 1,000,000 times weaker. There's so many different strengths it could have had. But here's the weird thing, and if you want to sprinkle in a pixie dust of God, you can, and if not, I understand. All the forces are perfectly strengthed to create this universe. In other words, in order to create stars and planets and life, none of them could be off by 0.001%. It's like something new, and if it didn't know, then the randomness, the random chance of making a universe where the forces are perfect is so bizarre that it's outlandish to imagine. Does that make sense? And how many parsecs is the sun? Well, you do decimals, because a parsec is 19 trillion miles, and the sun is 93 million miles from us. So it's not even 1 parsec. I'll let you work out the math. A parsec is 19 trillion miles. The sun is only 93 million miles away from us. All right. So we're looking at the fate of the universe now. What's going to happen to it? And we don't know. We're not too sure. No. 1,000,000 what, Brody? A parsec is 19 trillion miles. It's in the study guide. In the middle of universal expansion still occurs. Second page, all in bold. Take a look at that while we move along. A parsec is 19 trillion miles. All right. Second page, study guide, middle, all in bold. Definition of a parsec. Definition of a megaparsec. And then the sun is 93 million miles. No, oh dear God. Look, everyone turn to the second page. No, a megaparsec is not 1,000,000 miles. A parsec. Not 1,000,000 miles. A parsec